So we're talking about the power method. Power method is a way to compute eigenvalues and eigenvector, but it's only gonna help you compute the dominant eigenvalue, right? So the thing is, this is an assumption that the first eigenvalue, the modulus of the first eigenvalue, has to be strictly greater than the modulus of the second, the absolute value of the second eigenvalue. If it is a repeated eigenvalue, and that to the greatest, if the biggest eigenvalue is a repeated eigenvalue, we will not be able to find the eigenvector. And why is this a condition? Well, if you look at the algorithm, what this algorithm does is applies the matrix A and normalizes. So all it is doing is taking up, let's say, any vector, and it repeatedly applies my matrix A to that vector and normalizes. So what the hope is that after, let's say, a million iterations, I would have applied that matrix to this vector so many times that my matrix has dominated the computation in the direction of the dominant eigenvalue. So the only that direction remains while I'm applying the matrix again and again. So let's see the proof of this. This is basically the power method, that I take an x naught, I apply a to the a to k times, and then I normalize it. So if A is diagonalizable, with n linearly independent vectors, I can use them as basis. I'm not saying it's a perpendicular basis. I'm not saying it's an orthogonal basis, but it can be used as a basis. So I write my x naught as alpha times that vi, right? Now, because this similarity transformation exists, ak x naught is lambda k lambda this quantity applied k times v lambda v inverse to the power k. But because v inverse will get cancelled again and again with v, it only becomes v lambda to the k v inverse. So applying it to x naught, I can see that v inverse x naught will only be these coefficients. Coefficients applied to lambda k will only multiply each coefficient by its own power, and then again, bringing the v in from this side. So my ak becomes, if I take lambda 1 common, it becomes v1 plus alpha I upon alpha 1 lambda I upon lambda 1 power k vi. Now if my condition was true, that lambda 1 was strictly greater than all the other lambda i's, for k tending to infinity, this number will go to 0. So my direction finally will become only the direction of v1, and my eigenvector will become the direction of v1, and my eigenvalue will become the direction of lambda 1. That's it. So if I denote this by yk, I denote my xk by divide by the norm, and yk tends to 0 as k tends to infinity, and therefore my vector goes in the direction of the dominant eigenvalue, and my eigenvalue is just that dominant eigenvalue. Next is, what is the convergence rate of this algorithm? Obviously, one thing is, you can understand, if there were two eigenvalues if there were two repeated eigenvalues, one would not know. For example, if this is a space and I keep applying A again and again and again, there will be two directions in which the matrix has the same effect. So one will not know what is the eigenvector here actually. So one cannot make any comments about convergence, and that is true. So if my lambda 1 was strictly greater than lambda 2, my convergence in the eigenvector is lambda 2 divided by lambda 1 power k. So it's a k it's a linear. At k iterations, my order is lambda 2 divided by lambda 1 raised to power k. It's a linear. But my eigenvalue will be, and my computing of the eigenvalue will be this squared if it's a So yeah, I obtained my eigenvector. From that I obtain my eigenvalue. That's an estimate of my eigenvalue, and I can check the residual. And before we did talk about the bounding of the a posteriori bounding of my error, and I can use that when my error becomes less than, let's say, a tolerable amount. I can conclude my algorithm. So there is a posteriori estimates help us make stopping conditions. A posteriori error estimates. Like I was saying, this convergence is linear with the number of iterations. If A is normal, then the eigenvalue estimate converges a bit faster, but still linearly. That means it's a square. The eigenvalue estimate converges a bit faster, but still linearly in the method, in the number of steps. The power method is fast when the dominant value is well separated from the rest. When the dominant value is well separated from all of the others, this ratio is smaller and it converges faster. The conclusion is rather general for all iterative methods. Convergence is often good if eigenvalues are well separated and bad otherwise. It's a condition. And the power methods is too slow to be typically used in practice. So we go to the other one, which is the inverse power method. One thing which motivates the idea of the inverse power method is, for example, if I have let's go to the board. Why would one want to try something else? Well, the idea is that the convergence depends upon lambda 2 divided by lambda 1, right? The ratio of the eigenvalues. So what if I could create a matrix which has the same eigenvectors, but their eigenvalues are changed in such a manner that this ratio becomes huge. So that's what I would do. Let's say I have mu, a number mu, that's it. I create a matrix A minus mu I inverse. Now A minus mu I inverse, I claim has the same eigenvectors as the eigenvectors of A. Let's see why. A minus mu I inverse x should be equal to some let's say beta times x. Not the same eigenvalues, but the same eigenvectors. And let's expand it. So A minus mu I take the inverse that side, x is equals to A minus mu I beta times x, where beta is just a scalar, right? So let me open it up. Ax minus mu I beta x, so minus mu beta x. So this becomes x is equals to, and if now my claim is that x is same eigenvector of A, so this becomes Ax equals to, let's say, some lambda times x, lambda x minus mu beta x. Therefore lambda minus mu beta will become 1. So yeah, where beta is the eigenvalue of this, eigenvalue of A minus mu I. The idea is that the eigenvectors of A are also the eigenvectors of A minus mu I x. A minus mu I basically, because this held in this direction. Let me try to prove it in this direction. If Ax equals to lambda x, this is the eigenvector of A. Now I want to prove that this is also the eigenvector of A minus mu I inverse. So let me write A minus mu I x will be equal to lambda minus mu x, right? All I did was subtracted mu x from both sides, and yeah, taking the inverse in that direction, my eigenvalue becomes 1 over lambda minus mu x is equals to A minus mu I inverse x. So So A minus mu I inverse x is 1 over lambda minus mu. That's what I'm saying. The eigenvectors of A minus mu I are the same as the eigenvectors of A, and their eigenvalues are 1 upon lambda minus mu. 1 over lambda minus mu, that's what we've said. So now what was the point of all of this? The point of all of this was, if I can choose my mu closer to the lambda that I want to calculate, 1 over lambda minus mu will become huge, because this number will be very small. So the greatest eigenvalue lambda 1, or let's say lambda 1 for this particular matrix, will become much higher than the lambda 2, all of the other lambdas. That's what I'm saying. If I have a good estimate mu of an eigenvalue lambda j of a matrix A, then this number, the eigenvalue of all other eigenvalues lambda j minus mu inverse, all other eigenvalues divided by the greatest dominant eigenvalue is much less than 1, because this number is huge, this number is greatest. This is a big number. So doing a power method on this particular matrix will converge really fast, because this is very well separated. So all I have to do is find a good estimate of the lambda j and do it, right? That's the idea. Now this eigenvalue estimate is something that was very in the air, right? How would one know a good estimate of the eigenvalue? What one can do is use the power method to compute the eigenvalue estimate. So what one does is choose a starting vector. This is one of the Rayleigh quotient iterations. Choose a starting vector x naught, with there x naught is 1. Compute lambda naught, which is the first estimate of my eigenvalue, as x naught transpose a x naught, right? Then use that use this lambda naught in the inverse power method, a minus lambda I x equals to x, to calculate the eigenvector, normalize the eigenvector like a normal. This is normal inverse power method. Now compute lambda k plus 1 based on this new estimate of the eigenvector. So what we are doing is, in Rayleigh quotient iteration, using inverse power method to compute eigenvector, using eigenvector estimate to compute eigenvalue, and using eigenvalue estimate to compute eigenvector from the inverse power method, by using that eigenvalue estimate as a minus mu I in my inverse power method. So that was the power method. Now we are going to talk about another algorithm which gives us, now the downfall of power method is that it will only give me the dominant eigenvector and the dominant eigenvalue. But if I would want to know more, I would need some other algorithm, because what happens in the power method is I'm applying A again and again and again, and all of the other relevant bits, all the other relevant eigen expression gets diminished and goes to 0 with k tending to infinity. The QI algorithm is different.